So far, we have looked at the basic mechanism of finite element analysis using spring as simple example. But in the real application, a more realistic model for an element is what we call a truss element. So typically, you can think about a truss element as a bar structure, right? So far, if you recall the spring, what you see there is we only consider the spring constant as the basic property of the element. But when you go to a realistic structure, you will have an element that has three-dimensional shape. So the more realistic way to represent the element would be a bar structure where the bar has a finite length, has certain cross-sectional area, and you also have some mechanical property, typically governed by its Young's modulus. So Young's modulus governs how much the material will deform when the material is subject to external loading. Okay, based on this understanding of the truss element, right? We will assume that in truss element for finite element analysis will have the following characteristic to make the model tractable. Okay, first of all, this bar is geometrically straight. Okay, so it has a very simple geometry shape and it has a simple uniform cross-section area. Whether it's being round shape or square shape is not critical as long as the distribution of the cross-section area and the mass is uniform across the element. Okay, and the material obeys Hooke's law. That means it will elastically deform and the deformation grows linearly with respect to the external deformation. The forces are applied at the end of the metal bar, so there's no other forces being distributed in the middle, right? Basically, what that means is that the node for your finite elements are only occur at the end of this truss element, right? After all, this is what we want to do. We don't want the element with any other forces in the middle. That means we have to further subdivide the element to even smaller manageable part. Right? So this is a very important assumption, right? And the bar support axial loading only. By that we mean that if we apply a force to the element, we only go along its axial direction. We are not twisting the bar such that it will start to have rotational motion within the bar, etc. So those forces are not allowed in the bar. There might be cases in a more complicated situation where you will have these torsional forces, but for this course and for truss element, we are only consider the forces loading in the axial direction. So all the deformation will be occurring along the axial direction. Right? What does that mean? That means even though the force may be applied at the angle to the truss element, the element will only deform vertically. It won't deform under this way. Okay, so we'll see some example of that later in the lecture. And so the only thing we need to modify from a spring model to a truss element model is how we define the stiffness matrix K, right? So in the truss elements, what we can work out is the value of the deformation of the truss element under external loading. So the deformation delta when the element is subjected to an external loading P is given by this formula here, where P is the load, L is the length of the element, right? divided by A, which is the cross-sectional area of the element, and E is the Young's modulus, the elastic modulus of the material. So PL divided by AE is the deformation of the element under external loading. Now, if you recall that the spring element, the spring constant is basically the force divided by the displacement, we can do the same thing to define the effective spring constant K for this truss element, which is basically P over delta. Now, if you plug in the value of delta from this equation to this function here, you'll find out that K, the force constant of this truss element, is AE over L, right? So if you have a single truss element, right, then the stiffness matrix, if you go back to a few slides ago, what happened to a single spring, you will have what, K minus K minus K, right? That's the single spring. But now we know K is AE over L, so we can take that AE over L outside of this matrix. Then this effective stiffness matrix for the truss element will become AE over L times this matrix 1 minus 1 minus 1, 1. Right? And equivalently, the equilibrium equation for the matrix that governs the deformation with external force will be this guy times the displacement at the two endpoints of the truss element, which equal to the force applied on these two elements, right? So in this case, if you look at what happened to a uniaxially loaded bar, in the spring case, in the spring, one-dimensional spring case we just looked at before, we will have two elements at the two ends where each of these nodes will have external force F1 and F2 being applied to the nodes with a corresponding displacement U1 and U2 at these two nodes, right? In case of a uniaxially loaded bar on the truss element, the force and the displacement at the nodal point will be the same, right? This is the basic setup as we've seen before. The only thing that changed, as we'll see in the previous, as we saw in the previous slide, is that before the spring has only a single spring constant K. Now we have a uniform cross section of the bar, which is A. It has a length which is L, and a Young's modular which is E. Now in this case, this K value for the spring will be replaced by this quotient AE over L, which governs the stiffness of the metal bar. So there's nothing fundamentally different between these two cases, right? The only thing makes it slightly more complicated is you change a single value K to a quotient AE over L for this metal bar, which they both govern the fundamental mechanical property of the finite element.